Hello everyone and welcome to my channel. This is an educational channel and today we are looking at the reciprocal system of theory from one Dewey B. Larson. This is our 443rd video on that topic, and Mr. Larson was an American engineer who in 1959 proposed his two fundamental postulates, two sentences about how he believed that the universe operated, and then he elaborated on those through a process of deduction, if this then that type of approach, and arrived at his theoretical universe, what his universe would look like if his postulates were correct. And then he compared his theoretical universe with the empirical, measured universe of the legacy scientists that they have compiled in their tables, scientific tables. And we're looking at one of those results today, his book called Basic Properties of Matter. And this book looks at chemistry in general, and Larson derived many different equations for some of the basic properties of matter, for compounds and atoms, and he goes over those equations, how he derived them, and then compares them with the results that the scientists got. Today we're looking at chapter 5, which is entitled Heat, where he looks at some of the specific heat and some other quantities that he arrived at equations for, and then how he did that, and what the results look like. Okay, now Larson's the reciprocal system is also known as the universe of motion. Larson was one of many scientists who have attempted to construct their universe upon motion. In Larson's, one of his first postulate, he says that the universe is composed entirely of motion. Now, what kind of distinguished Larson from many of his predecessors who attempted to construct their universe on motion but failed is that Larson defines motion. More specifically, he defines motion as the relationship between space and time. Or he says, two reciprocal aspects, space and time. So space and time have are the two components of motion, and motion is the relationship between space and time. Motion is basically a fraction, with space or time as the numerator, time or space as the denominator. And you can see that in the most simple kind of motion that we have, speed. The bike is going 10 miles an hour. 10 miles of space in 1 hour of time. Space over time is speed. But if you decide to double the speed, you can now say the bike is going 20 miles per hour. 20 miles of space in 1 hour of time. But equivalently, you can also say the bike is now going 10 miles per half hour. So you can either double the space or halve the time. That is a reciprocal relationship. So you can see the reciprocal relationship in speed. Larson spreads that out and generalizes it to be all of our scientific phenomena are relationships between space and time. Not just speed, but also things like matter and energy and force and electrical charge or electrical capacitance, magnetic flux, permeability, power, pressure. All these different phenomena are expressible in relationships between space and time. Now, another part of Larson's postulate is that, the first postulate is that motion, space, and time all come in 3 dimensions. So you don't have just time over space or space over time. You also have the various permutations of those with 1, 2, or 3, or even more dimensions. So, motion, speed is space over time. Turns out that energy is time over space. But then more complicated motions are matter, time to the 3rd power over space to the 3rd power, or pressure, time over space to the 4th power, or density, time to the 3rd power over space to the 6th power, and so on and so on. So space, time, and motion come in 3 dimensions. They also come only in discrete units. You have to have a full unit of space before you have space. You have to have a full unit of time before you have time. If you don't have a full unit, then you don't have it. And you don't have that entity. If you have exactly 1 unit of space in 1 unit of time, space over time being speed, you have what Larson calls unit speed. This is the unit of speed. 1 unit of space and 1 unit of time. Parenthetically, this unit of space is about 1/500,000th of an inch. The unit of time is approximately, it's 1.52 times 10 to the minus 16 seconds. And then if you take 1 over 1, you get 1 unit of speed. And that's also known as the speed of light. Now, if you study the reciprocal system, you have to accept the idea that space and time, motion, exists before anything that would be moving. Motion exists prior to the thing moving. In a universe of motion, it makes sense. And so this motion at the speed of light is the what Larson calls the default speed, or the null speed, the 0 point, the neutral point of this universe. Now, another thing that I haven't mentioned yet is that when Larson is talking about motion, he's really talking about what he calls a scalar motion. This is a more generalized kind of motion than what we're familiar with. Normally, we talk in terms of vectorial motion, motion that has a direction, a specific direction that you can assign it. The speed becomes velocity when you give it a direction. So you say the bike is moving 10 miles per hour south. That would be a velocity. But without the direction, it's what he calls a scalar motion. And you can really envision a scalar motion if you take a balloon and you put some dots on it with a magic marker. And if you blow up the balloon, all of the dots will be moving away from each other, but they won't be moving in any specific direction. They'll just be moving away from each other. Every dot will be moving away in every direction from every other location. And so that is not a vectorial motion. It is a scalar motion with no specific direction. That is the source from which Larson builds his universe of motion. And that analogy, then, if you take that at the speed of light, at unit speed, that is the background speed of Larson's universe. So it is omnipresent and eternal. It's always there. It's always going to be there. That at all points in the universe, there is a motion outward at the speed of light in all directions. And then basically the reversal of that motion is what's going to create the phenomenon or the phenomena in the universe, including matter, energy, force, and pressure, and all these other things. And so that is unit speed outward at the speed of light, 1 unit of space and 1 unit of time. And given that speed is the neutral point or the midpoint of the universe, that means that half the universe is moving faster than that speed of light, half is moving slower. Larson refers to these as the cosmic sector and the material sector, respectively. In the material sector, the slower than light sector that we're familiar with, we have relations that are based on 3 dimensions of space and vectorial space and scalar time. This happens basically through abstraction. When you take that outward motion of the balloon, you don't have any type of direction. But if you arbitrarily decide that you're going to stop the universe, or you're going to make some kind of a snapshot or some kind of a way of measuring, you can arbitrarily decide that one of the dots is motionless. And when you do that, then you can start figuring out the directions. And that is really what happens in what he calls the spatial reference system. In the spatial reference system, you stop the universe and then you start reckoning the directions. And that is 3 dimensions of space, X, Y, Z coordinates in a still frame. You've stopped that dot. And so you're measuring on that still point, the arbitrary still point that you've assigned. You're measuring your space, and space now becomes vectorial or directional as opposed to scalar. But time is still scalar. Time is still ticking or flowing. It's always getting later and later and later, but it's not moving in any specific direction. So you have a vectorial space and you have a clock time. Larson calls that coordinate space and clock time. Now, if you move over into the cosmic sector, where speeds are faster than unity, or faster than the speed of light, which incidentally is blasphemous to the legacy scientists who believe that the speed of light is the maximum speed of the universe. So they don't know anything about the cosmic sector. But if you move over to this cosmic sector, then you have the reverse. You have what he calls a temporal reference system. This is when you abstract the world in time instead of space. You say that this spot on the balloon is motionless in time, arbitrarily, and then you start measuring the directions in time, you find that you have 3 dimensions of vectorial time, what he calls coordinate time. And now these directions are not directions in space, but they are analogous to or reciprocals of directions in space. And then you have what he calls clock time. The time is always getting farther and farther and farther apart. So it's the inverse. When you cross that boundary, the speed of light boundary, you have to interchange the functions of space and time. So in the material sector, you have coordinate space and clock time. In the cosmic sector, across that boundary, you have coordinate time and clock space. Now, within the material sector and the cosmic sector, you also have the discrete unit postulate in play with that boundary is the unit speed boundary. But within the material sector, you have what he calls the unit space boundary. Within 1 unit of space, 1/500,000th of an inch, you have interactions that are like particles and atoms and molecules. And they occur within 1 unit of space. If you don't have a unit of space, then you don't have space. And if you don't have space, then you only have time, because the universe is made out of space and time. And so Larson calls this the time region. And in the time region, you have these interactions of subatomic and microscopic particles. But they do not occur in space. They occur in time. And when you cross that boundary, you have to invert the rules again. And so instead of the progression moving outward, and its opposite, which he calls gravitation, moving inward, as you do have in the outside region of the time region of the material sector, you have the progression now moving inward and gravitation moving outward. And as a result, the progression being a constant, always there at the same magnitude motion of the inward motion, finds an equilibrium with the gravitation, which is adjustable or variable depending on the inverse square law. And there is a point at which those 2 forces are equal, and that is the equilibrium distance that atoms in the solid state find themselves. And then the same is true over in the cosmic sector, except now you're dealing with cosmic atoms and cosmic molecules instead. And they find their equilibrium in what he calls the space region, in which you don't have a full unit of time because the interactions are occurring in less than 1 unit of time. And therefore, you have only space. And in that space, now the progression is going inward and gravitation is going outward in time. So in the material sector, we only see space because we're anchored to the spatial reference system. In the cosmic sector, viewers in the cosmic sector only see time because they are anchored to the temporal reference system. So when something goes on in the time region or the space region, they would see it, they would see it as a reciprocal or as the inverse. The interactions are occurring in the material sector, the interactions are occurring in time, but we see it in what he calls equivalent space because we don't see time. We see the inverse of what's going on in time in space, but it's really going on in time. But when we see that, we see it's reduced by what he calls the interregional ratio, which is the amount that's lost in the translation when you cross a boundary, when you observe across a boundary. And then it's also viewed as a second power entity, whenever we look into equivalent space, we see a second power entity. Okay, now atoms are basically formed from, like I said, reversing this original space-time progression. First, you have to reverse, you have to slow it down and stop it, and then you have to reverse it. You're basically moving from an outward motion of that balloon to an inward motion of that balloon. The inward motion is gravitation. So gravitation is inherent in matter, whether you're talking about subatoms or atoms. Those are come about through rotating that original the photons, and the photons are a result of neutralizing that outward motion, or basically a photon is a simple harmonic motion, a wave-like motion. You can envision it as being like a wave-like motion occurring on the surface of the balloon. So the balloon is still expanding at the speed of light in all directions, but this other motion, this wave-like motion, is manifesting on the surface of the balloon. So you can still see the photon as moving at the speed of light in all directions, but you can also measure its frequency, which is the speed at which it's vibrating. And then you take those geometrical considerations, make it so that you have two photons that vibrate around the same central point. And then those two photons need to be rotated in 3 dimensions to make an atom. And those 3 dimensions are really the numbers of Larson's periodic table. So if oxygen is number 8 in the periodic table, it has a 3-number combination in Larson's system: A, B, and C. A and B are two-dimensional rotations, and C is a 1-dimensional rotation. A and B alternate with each other, and really can be 1, 2, 3, or 4, and 5. And then the C number can be 0 in the noble gases, and it can be positive or negative. So now let's start going through a little bit of Larson's chapter on heat. And you know, he kind of gets into the weeds on this stuff and gives you a lot of details, but it does kind of show how he's thinking about these different issues, kind of in the context of what we were just talking about. In order to establish the relation of the Kelvin scale, the absolute temperature scale that he was just establishing in the last episode, Kelvin scale to the natural system, like in Larson's system, he's got a natural system for everything, and that is based on space and time. So, you know, the natural unit of speed is 1 unit of space in 1 unit of time. Energy is time over space. So the natural unit of energy should be 1 unit of time in 1 unit of space. The natural unit of mass should be time to the 3rd power over space to the 3rd power. So natural unit of time taken to the 3rd power over a natural unit of space taken to the 3rd power. And so temperature, I believe, is time over space. And so this is how he would establish the natural system of reference. And he's comparing it to the Kelvin scale, which is based on water, and the melting point and the boiling point of water are 100 degrees apart. It will be necessary to use the actual measured value of some physical quantity involving temperature, just as we have previously used the Rydberg frequency, the speed of light, and Avogadro's number to establish the relations between natural and conventional units of time, space, and mass. The most convenient empirical quantity for this purpose is the gas constant. It will be apparent from the facts developed in the discussion of the gaseous state in a subsequent volume of this series that the gas constant is the equivalent of 2/3 of a natural unit of specific heat. And again, the specific heat is the increment of heat you need to raise a certain quantity of matter by a certain temperature. We may therefore take the measured value of this constant, 1.9869 calories, or 8.31 times 10 to the 7th ergs per gram mole per degree Kelvin, to make it as confusing as we can, as the basis for conversion from conventional to natural units. This quantity is commonly represented by the symbol R, the gas constant, and this symbol will be employed in the conventional manner in the following pages. It should be kept in mind that R equals 2/3 of a natural unit. For general purposes, the specific heat will be expressed in terms of calories per gram mole per degree Kelvin in order to enable making direct comparisons with the empirical data compiled on this basis. But it would be rather awkward to specify these units in every instance, and for convenience, only the numerical values will be given. The foregoing units should be understood. So that paragraph there is kind of just enough to eliminate your average person from understanding this. And I don't really think it's necessary for Larson to do this, but Larson is writing for an audience of scientists, and the scientists generally understand this stuff in that way, and he's trying to relate to them. I think he would have been better off trying to establish his natural units without regarding the conventional units. But I could be wrong, and maybe I just need to suck it up and try to figure out the entangled way that the scientists have measured it. Okay, dividing the gas constant by Avogadro's number, which is 6.02 times 10 to the 23rd per gram mole, we obtain the Boltzmann constant, the corresponding value on a single molecular basis or single molecule basis, which is 1.38 times 10 to the minus 16 ergs. Because we took that number 6.02 times 10 to the 23rd, and we divided it by 4.56 times 10 to the minus 8, which is the unit of space. As indicated earlier, this is 2/3 of the natural unit, and the natural unit of specific heat is therefore 2.07 times 10 to the minus 16 ergs per degree. We then divide unit energy, which he says is 1.49175 times 10 to the minus 3 ergs, by this unit of specific heat, which gives us 7.2 times 10 to the 12th degrees Kelvin. That's 7 trillion degrees is the natural unit of temperature in the region outside unit distance. That is for the gaseous state of matter. Outside unit distance means outside the time region. So the gaseous state of matter is outside the time region, whereas the solid state of matter is inside the time region. But he just bypasses all of this, and just it's almost kind of like obfuscation, where but I don't think he is obfuscating. He's just trying to make it simpler, and he's trying to put it in the wheelhouse of a scientist. But in doing so, he just makes it completely opaque to somebody who isn't familiar with all these numbers. But just be okay with his with being confused and move on. And maybe through detective work, we'll be able to figure it out at some point through other things that he says. We will also be interested in the unit temperature on the time to the third power basis, the temperature at which the thermal motion reaches the time region boundary. So the third 3/4 power of 7.2 times 10 to the 12th is 4.39 times 10 to the 9th, or 4.4 billion degrees. But the thermal motion is a motion of matter and involves the 2/9 vibrational addition, this comes from the photon, to the rotationally distributed linear motion of the atoms. This reduces the effective temperature unit by the factor 1 plus 2/9, the result being 3.59 times 10 to the 9th degrees Kelvin. Now, those two paragraphs, Larson should have taken an entire book to explain those two things. And if you read that book, then you could have understood what he's talking about. But instead, we'll just try to move on. Actually, we're not going to move on. We're going to stop there, and we will start up again tomorrow. But basically, Larson is attempting to set up the units of temperature here that he's using. And depending on whether you're within the time region, whether you're outside the time region, or how many dimensions are in or outside the time region, then you have different units of temperature. These units are astronomical. In the gaseous state, the temperature, the unit of temperature is 7.2 trillion degrees. Why he establishes that like that, I don't get it, and I would really like to, because I've read this book over and over again, and I still don't get it. So if anybody gets it, please explain it to me, and I can impart it, that wisdom, to somebody else. Again, these two chapters, chapters 4 and 5 of this book, are the hardest chapters that I've ever read, and probably any book that I've ever read. Okay, thanks for tuning in today.